Alright, now that you understand the basic premise of the logic gates from the previous video, we are now going to start to look at Boolean algebra, and that's what these next two videos will be about. So this is part one of Boolean algebra. So the first thing we are going to do is we are going to look at the NAND and NOR gates, the last two gates that we did not look at in our previous video due to time constraints, and then we're going to dive right into the first part of Boolean algebra, just the basic properties, those that you probably know from regular algebra. Alright, so I'm sure that those of you who have been watching these videos remember that in the previous video we ended on the equivalence gate, which I had mentioned is just the XOR gate mixed with a NOT gate together. Well, we have two other gates that we can mix NOT gates with in order to form new gates. In this case, they are the NAND and the NOR gates. Let's take a look at the NAND gate first. The NAND gate is simply an AND gate plus a NOT gate to form a NAND gate. With a NAND gate, if both inputs are 1, the output is 0. Otherwise, the output is 1. This is clearly seen from our truth table that it is the exact opposite output of an AND gate. And it is also written as x equals, and then within parentheses, AB or ANB, and then we just add the little NOT, whether you want to use the bar or the apostrophe. I'm going to use the apostrophe in our videos. Similarly, a NOR gate, which is simply an OR gate combined with a NOT gate to form a NOR gate, is done like so. If one input is 1, the output is 0. Otherwise, the output is 1. The exact opposite of an OR gate, and it is even written as such, where we just take the A plus B, place parentheses around it, and then add our little NOT gate. Now you may think that NAND and NOR gates are a little bit more complicated than AND and OR gates, but believe it or not, the NAND and NOR gates are basic blocks and basic blocks in your chipsets that you'll be using in engineering labs, not the AND and OR gates. And I will explain more as we go much, much deeper into digital engineering. Okay, so let's get right to the nitty-gritty with Boolean algebra. The first equation that I had mentioned I had done back in the previous video, which was x equals a. Simply, if x is 0, a is 0, and x is 1, a is 1. This is the most simple equation that you can possibly use for Boolean algebra. Let's take a look at four equations that are a little bit more complicated. So let's take a look first at 0 and a. If 0 is ANDed with a at all, the answer is 0. And if 1 is ANDed with a variable a, the answer is the variable a. So if the variable a is 0, 1 and 0 is 0. And if the a is 1, 1 and 1 is 1. It's pretty simple to take a look at if you take a look at our AND gate here. So let's just take a look at our AND gate, and you can see 0 and a is 0. Let's just say a is equal to 0, and b is our unknown variable. And you can see that no matter what we use, the answer is 0. Similarly, we use 1 and b in this case. So we just use a equals 1, and b becomes the variable. And we notice that the output is equal to the variable. Our two OR gate equations involve 0 or a. When 0 is ORed with a, the answer is the variable a. But whenever 1 is ORed with a, no matter what, the answer is 1. Let's take a look at our OR gate now, and you will see with our truth table, we're going to use a as our fixed variable, which is 0, and b is our unknown variable. And you notice that every time a is 0, the answer is the variable. So in this case, b can be 0 and the output is 0, and b can be 1 and the output is 1. In the case of a equals 1, no matter what b, our variable is, the output is 1. The next four equations involve a variable being dealt with by itself and an ORed by itself. In the first two equations here, we have a ORing with itself, which is a, to form a. Obviously, this is pretty obvious. If a equals 0, 0 plus 0 is 0. And if a is 1, 1 or 1 is 1. In the second equation, a ORed with its opposite always equals 1 no matter what. This is pretty obvious too, because a's opposite will only have to be one other variable. So if a is 0, for example, the opposite of 0 is 1, and no matter what, you have 0 ORing 1, and 0 OR 1 is 1. Similarly, with the AND equations, A ANDing with itself forms A, no problem there. 0 and 0 is 0, and 1 and 1 is 1. And if you take the variable and you AND it by its inversion, no matter what you're doing, you're taking 0 and 1. And what is 0 and 1? Well, the answer is 0. I'm going to stop here for a little bit just to remind you that if you are confused with any of the equations here, please just pause the video, go back, rewind, do what you have to do, because these equations eventually build up on each other, and they're going to build up very quick over the next 2 to 3 videos. So with that, let's do a high school algebra review. First with the commutative property. Just like you did in high school algebra, 2 plus 3 was equal to 3 plus 2, the commutative property also applies in Boolean algebra. 1 or 1 is always equal to 1 or 1, 1 or 0 is equal to 0 or 1, 1 and 0 is equal to 0 and 1, like so. Also, the associative property also applies. And there you can see in proof with numbers as well. Now here's another question. Does the distributive property apply in Boolean algebra? Well, let's take a look. Let's take A or B ANDed with C. Let's plug in some numbers. I'm going to make A equals 1, B equals 1, and C equals 0. 1 or 1 ANDed with 0 basically makes 0. And now I'm going to take its distributive property, which would be AC plus BC. Basically, you're just taking the C and applying it to both A and B. And we take a look and we notice that 1 ANDed with 0 is ORed with 1 ANDed with 0, and the answer is 0. So yes, it looks like the distributive property does apply. Let's go back to a NOR gate. Well, with this NOR gate, we can actually simplify it a little bit further so that we do not even need the parentheses in this level. We can do this by performing a property known as De Morgan's law. In De Morgan's law, we can invert all the Boolean variables that is currently in the current equation. In this case, A naught becomes A and A becomes A naught. And then we flip all the AND gates to OR gates in the next level down only, and vice versa. And I'll explain what I mean about that later. So in this case, De Morgan's law tells us that A plus B naught becomes A naught ANDed with B naught. If you fill out the truth table for A naught ANDed with B naught, you notice that it is identical to A NOR B. One thing that I mentioned about De Morgan's law is that you can only invert all the variables that are in the current level. So like for example, I'm going to take this one right here. The B or C is actually a level down from the A. It's actually one variable in itself in the current level. So what you do is that you invert the A and then you invert the B or C as a group. You leave the B or C alone. And then of course you flip the OR gate and you turn it into an AND gate. Finally, we're going to take some of the easy stuff that we have learned and we're going to do something a little bit harder. Let's take a look at this one, A ORed with A and B. Well, logically, if the output is true, only if A is true or A and B is true, well, if A and B is true, then obviously A has to be true. So this is what we consider a redundancy, and the answer would have to be A. But we can prove this by using a distributive property. With the distributive property, we just take A or AB, then we go ahead and factor out A or AB. We just factor out the A, and we are left with A ANDed with 1 or B. We know that 1 or B from the earlier in the video is always equal to 1, and A ANDed with 1 is always equal to the variable A. No problem there, right? Similarly, if we wanted to use the distributive property to factor out an equation like this, all we have to do is factor out the A, and we are left with A ANDed with B naught or B. We know that B naught or B turns out to be 1, and A ANDed with 1 again is equal to A. So these redundancies can be found very easily, and you can simplify your equations with very little trouble. Alright, so that's the end of this video. Thank you for watching. We're going to take a look at more of those redundancies. We're also going to take a look at consensus theorem next. And we're going to take a look at more about Boolean algebra. It's going to be about 2 to 3 videos long, and I hope that you bear with me. So please thumbs up, comment, and subscribe, and I hope to see you next time. Thank you for watching.